I'm really glad to be here and to be able to talk to you about Roger Penrose today. And actually, I'm a replacement of Professor Kałuszyńska, who was unfortunately in the very last moment unable to come, and she wishes to apologize to all of you for her not being here. But I decided to kind of kick in and present a topic which I think is, in some ways, is dear to many of us, because Roger Penrose was our guest many times, and he also was the guest here at this conference in 2010, which was specifically devoted to his thought. And I named this talk Roger Penrose, and I gave a question whether he is a complex Pythagorean. I'll get into in a moment what it means, and I did have a chance to talk to Roger about what he thinks about that, and he liked this idea of being named a complex Pythagorean. And my talk will be kind of to show you where I see that in the traits of his thought, you can actually find a justification for that. He was here with us last year in 2016 at the end of the year, presenting his new book. So that's the picture from that. That's actually not his book. That's actually my little book, but that's just a picture. And I thought it was funny. It's him on the picture and him on the page. So yeah, that's a bit of a memories from his last stay here with us. But today I would like to devote some time to explain why one could think that Roger Penrose is a complex Pythagorean, and why I think he could have liked that idea, and he did. That's why I decided to present this. I think I've mentioned this also giving a talk 7 years ago when he was here with us in Kraków. Okay, first let me just briefly mention what is meant, or what is implied by Pythagorean philosophy, because we have to explain these two elements. Why Pythagorean and why complex? Of course, complex means that Roger Penrose has a particular devotion to complex numbers. That's his philosophy, and he wouldn't even, I think he would even go ahead and say that's ideology. And we'll see that he operates with this ideology quite a bit, and quite a bit influences his thinking. So basically, this talk is to really show what influences the thinking of one of the famous contemporary physicists and mathematicians. And we all know that Roger Penrose, from his sort of first formation, is a mathematician. And he is a mathematician of very much of the Platonic orientation. And I was able to see different polls, statistics on how many mathematicians are Platonic, and it's about 3/4. So if you ask mathematicians what their position is, they would say 3/4 of them would acknowledge that they're really Platonic orientation. We'll see what that means in a second, because to speak about Platonism in the context of mathematics is a sort of a specific understanding, and I'll get into this in a moment. But generally, and even some physicists would say that, I think there's even a known phrase of Werner Heisenberg, that physics had made the decision for Plato. I think Heisenberg is known for having said that. So even physicists have a gut feeling that Platonic is better, at least for physics. But let's begin with a very brief one-page introduction to Pythagorean philosophy. Actually, if we talk about Pythagorean philosophy, I think some scholars are even not sure whether he ever existed. But we talk about something like a Pythagorean school, which was active in ancient Greece in 6th to the 5th century before Christ. And what they would claim is that numbers have spatial properties. I specifically stress that because we will see how close Penrose comes to this. That you would be able to see, I think he has a way of seeing and touching complex numbers. So I'll try to point that out. So that's this. And they literally exist in space. So for example, what Pythagoreans would say, if I have this piece of paper, it is this distance, let's say, exists really right? So it has an objective existence. I mean, we heard about existence just a minute ago, so I think it's confusing enough. But okay, so we understand it in this real old sense of having a extramental existence there in front of me. And what that means is, I know it's a contentious issue. Okay, then what was the important component here was the component of music, because spatial relations remaining in relations of rational numbers give us harmony. And this is something was very much appreciated by the Greeks, the musical harmony, and it was expressed, I think many of you could have dealt with a guitar, and you see that as you press the strings in steps related by rational numbers, then you get nice harmony. So I think this was a very appealing thing to the Greeks, and that's why another important term that will, of course, show up in thinking of Penrose will be this harmony. So I'd like you to keep in mind the two things that you can almost being Pythagorean means that probably you can touch these numbers, and I'll show you how close Penrose comes to this, and then that there is this component of harmony. That's a very important issue here. And for the Pythagorean school, number is the arche of reality. So meaning that the quantitative properties of things constitute their ontic foundation. And there are philosophers, for instance, a very well-known friend of ours, Professor Stanisław Krajewski from Warsaw, who talks directly about extended Pythagoreanism by claiming that not only numbers but also abstract mathematical structures can be considered to be ontologically fundamental. We all know and like that idea, so what would we mean by naming Roger Penrose a complex Pythagorean? We would say that he argues that complex numbers constitute the arche, the principle of reality. So this is what we will try to explore in this talk. Okay, and then there's a famous debate, a famous argument between Roger Penrose and Stephen Hawking, and even Stephen Hawking names Penrose directly a Platonist. We now have very different approaches to the world, physical and mental. Basically, he, meaning Roger Penrose, is a Platonist, believing that there is a unique world of ideas that describes a unique physical reality. I, on the other hand, am a positivist who believes that physical theories are just mathematical models we construct. So you can see that this debate between realism and constructivism kind of resonates here. And that it's meaningless to ask whether they correspond to reality, just whether they predict observation. So, I mean, some of you are aware of that big controversy between Penrose and Hawking, which led to the fact that they separated as far as their research goes, shortly following the paper on the space-time singularities. Okay, and this is normally what Penrose presents, and that's even his picture, done by his own hand. And he will claim that, I mean, he doesn't make a very strong claim. He calls these things mysteries, the word he likes very much. But actually, the fundamental ontology would split into three worlds: the Platonic world of mathematics, the physical world, and the mental world. Okay? I'm not going to be dealing with this today at all. I'm only be interested in that part. And for obvious reasons, the most fundamental for him is the Platonic world of mathematical ideas, which sort of generates this, and it comes back sort of to that. That's why these arrows are also important. And Penrose, it's important to know that Penrose qualifies these as mysteries. These are not proven or forever set categories for which you would have him crucified. No, he just claims these are the mysteries, and he takes it kind of with as a vision, I would say. Probably that's most you can say about it. Okay, and then what we have to say is that because there is a certain philosophical connection between Pythagoreanism and Platonism, in the fact that we should mention here the so-called Late Platonic School. Because in the early Platonic doctrine, we know that there was something like ideal numbers in the world of ideas, and they were the actual source of harmony, but mathematics understood as numbers applicable for computation was located below the world of ideas and was not intuitive, but in mathematics you could do the discursive, and you could use reasoning. That's the very Platonic and the normal, let's say, early understanding of mathematics. Then the Platonic school and Plato himself were very much influenced by the Pythagorean school. And that happens mainly due to two students of Plato, that is Speusippus and Xenocrates. And these two thinkers sort of reshaped the Platonic thinking on mathematics, and this is probably often mentioned as the source, the reason why today we talk about this ontology of the universe as being mathematical. So Speusippus would do the following. He would say that not the ideal numbers, but the mathematical numbers, which are subject of computation, are directly the objects of the Platonic world, or the direct inhabitants of the Platonic world, are directly the mathematical ideas which we use for computation, not the ideal numbers. And Xenocrates, we can name him actually the forerunner of the contemporary ideas of the mathematics of the universe, because he proposed that mathematics be an ontology, right? So this is an important transformation of the Platonic thought influenced by the Pythagoreans, and this is where we today find the sources, the beginnings of our thinking that mathematics can constitute ontology. So this is a very brief recap of the history of philosophy. And then if you maybe I'll make one more mention that actually the biggest, the place where this idea of Penrose's affection to the complex numbers is so deeply articulated is his famous book, The Road to Reality. I think this book is just all about explaining why complex numbers. So he'll go over all kinds of mathematical structures, physical applications to show that really this is the complex numbers that are at the bottom of reality. And he throws out probably fairly well-known in philosophy of mathematics, fairly well-known arguments for the mathematical Platonism, meaning that why we understand that the mathematical ideas have their own objective existence. And then first of all, he refers to the objectivity of mathematical truth and of mathematical proof. And he uses his own word, which is called unassailability. This is something close to necessity. So his thinking is that if you prove something mathematically, it's objective and it's necessary. And then the other argument he brings in from the area of mathematics is that the richness and sophistication of mathematical structures, which many of them are known to mathematicians with no applications in physics. So the quick thing to say is that, of course, the world of mathematical structures is richer than the world of its applications in physics. And this is actually what's depicted in that graph, actually showing that only a small section of the Platonic mathematical world constitutes the entire physical world. Right? So there's only a section of it englobes the entire physical world. So that's his basic idea. And then what is probably less known, because these are fairly well-known arguments of Penrose, which he presents practically at every beginning of his more popular book. But then he goes into more physical arguments, which are developed usually within the philosophy of science. And then he explains that there must be reasons why there's such a great empirical adequacy of theories formulated in the language of mathematics. And he actually shows different theories to point out that with the increasing, and then the second condition is important, and there's a few terms which he uses, and I will just point to them immediately. First of all, I already mentioned the sophistication. It's a fairly, I would say, not a very precise term, but he will very much use that word, sophistication of mathematical structures. What it means, I'll come to that in a second. And then he will say that he will be proving that the dependence of the precision of physical theories depends on the sophistication of the mathematical formalism that is used. So he will show that as we increase the sophistication of mathematical structure, whatever that means, I'll come to that in a second, we will get a better precision of the predictions of the theory. So that's another claim he makes. And then now in the book, The Road to Reality, he has the, I think, first 16 chapters devoted to what I have basically depicted here is that the general rule is that a mathematical structure is sophisticated when it is based on an entirely rich concepts that instantly yield all possible solutions for free. He uses that term really for free, and he sees many of these things first coming through simple examples, and maybe I'll use that example of the polynomials, which if you use the complex numbers, you get all the solutions immediately. So his idea is of the sophistication of a mathematical structure, if it's rich enough so that from that concept you get all possible solutions. And the very example that he probably likes the most are the holomorphic functions. The reason I mention this because he will always also call it a holomorphic philosophy, which already accents his sort of subjective predilection for complex numbers. So, because if you have a holomorphic function, then you probably, many of you as mathematicians, physicists know better than I, but if you have a first complex derivative, it implies the existence of all higher derivatives and the analysis of a given function. And Penrose loves this idea that if you have a complex function, then if you take a derivative, you get all the derivatives of the higher order sort of for free. So it's immediately guaranteed that they exist. We all know that it's not that simple for the real numbers. And then he goes over on things like hyperfunctions. You can really extend the class of functions to the minus infinity class. And he always, and one of the arguments is actually to show that, for instance, the hypercomplex numbers would not give us all these interesting mathematical and physical properties. Okay. And then there is there's quite a bit of mathematics on that slide. But then from holomorphic functions, you have a very important geometric connection, because holomorphic functions have their geometrical representations as conformal transformation. And this is, again, the thing that Penrose likes very much, because holomorphic functions as mathematical structures, they get very quickly geometrical representations as conformal transformations. So they have preserving the angles between curves, to put in the shortest terms. And then he, of course, refers to the conformal structures of general relativity, that is preserving the structure of light cones and is reflecting to the motions of massless particles, meaning photons. He has a big section on that as well. I don't have time to go this. And then he's also preoccupied with projective geometry, which is the Euclidean geometry equipped with the points in the infinity. So he actually very much deals also with the notion of infinity. And then the very representation of complex numbers, which fulfills all the conformal geometry, is the Riemann sphere. I mean, if you open up his road to reality, the Riemann sphere is everywhere. And there's a particular reason why it's so useful for him, because it lets him represent the complex numbers in a geometrical way, and that's the key issue here. And for Penrose, the Riemann sphere also will provide a link between quantum mechanics and the space-time structure, and will be central to the formulation of the twistor theory. Twistor theory is his proposal of quantum gravity, which, from what I have seen, maybe some of you, I'm sure, know better, did not really survive on the market, and I don't think it's continued much anymore for all different particular reasons. That's not subject of my talk today, but just that's actually the presentation of the Riemann sphere. And this is basically, it's also a Penrose's drawing. What is the basic idea of theory, or the twistor theory, is that you replace the space-time, the basic structure of space-time, you replace with rays. So actually you get this correspondence between, you turn light rays into points, and then from all these rays you get a representation in the Riemann sphere. So that's fundamental for him, and that sits at the bottom of the idea of the twistor theory. And what is the most important is that if we have a special theory of relativity, then we can also apply the Lorentz group, which also has this conformal structure there, and then you can actually, and this is where really the Pythagorean moment comes. Penrose claimed that you can really depict or equate the Riemann sphere with the celestial sphere. So you can practically see that geometrical representation of the complex numbers. See and almost touch that representation. So in that sense, I think he comes very close to the idea of being really a complex Pythagorean, right? So, so this idea sits very deeply at the bottom of his idea of twistor theory. And then I have the, and then we come to development of this whole argument of the harmony, because Penrose very much is devoted to the idea that the complex in hylomorphic structures resonate with the nature very well. So again, you have this sort of now in abstract terms, but still the antique idea of resonance as being in touch with the harmony. So here I have the whole list of what the different complex structures do and how they resonate with nature. I probably won't read them. First of all is the representation of the Minkowski space-time in the form of a Riemann sphere, as the twistor space demands that the space is four-dimensional with Lorentz metric. So that's his argument why really these hylomorphic structures resonate with nature, because he takes the Lorentz metric for real, that it actually corresponds to special relativity, so he treats it as a real physics, and then it's the complex structures, the hylomorphic structures, that correlate, resonate with this to a very high level. Then you can have several ideas already within the twistor space, and he was getting certain very important results. I just don't want to read that mathematics, because probably it's known, understandable for most of you. The reason is that just it resonates well with nature. That's his basic, I would say, even Pythagorean idea. And then he ended up with very abstract structures with the sheaf cohomologies. And those were actually representing for him the much needed non-locality as a fundamental property of quantum systems. So he went as far as that far, and the discussion of this you can also see in the context of the twistor theory. And then there is another important sort of place, another important locus where you can see the influence, maybe not of really complex numbers, it eventually all ties together, but we have here a very, I would say, original claim of Roger Penrose that the second law of thermodynamics is a fundamental law. I mean, he defends that thesis in many of his books as well. And what he will claim is that he does these different calculations of entropy for different sizes of the areas in the phase space, and then he uses the Hawking-Bekenstein formula, and he ends up with the situation in which as you move along through the phase space with increasing entropy, then he ends up comparing the sizes of these phase spaces, and he comes to a conclusion that because the differences between these numbers are so huge, it's real. I mean, 10. You've probably seen these numbers: 10 to the 10th and to the, for instance, to the 23rd power, right? So that's unbelievably large numbers. And he draws a conclusion from this that it cannot be, I mean, of course it's philosophically questionable, but that's what he does. That because these differences in numbers are so huge, it cannot be only mental, but must be also extramental, meaning physical. That's his basic claim. Because just by making comparisons of the sizes of these different compartments of the phase space as you move along from lower entropy to higher entropy, and then his basic claim is that really the law of entropy, the second law of thermodynamics, is a fundamental law. So that's his basic claim, and then from there he ends up with also several of a very original and controversial idea in physics, which say that time is fundamentally asymmetric, and the Big Bang singularity had to be of a very low entropy, very uniform. And then there's this zero veil curvature hypothesis as a mathematical representation, expression of this idea that the Big Bang singularity had to be a very low entropy. And then, as I said, the ontology, actually, what he implies is that this is the ontology of numbers that is his main argument for the claim that the law of entropy, the second law of entropy, is the fundamental law in physics. And then he, of course, is able to introduce the arrow of time asymmetry, and the Big Bang singularity was of a very low entropy, very uniform. And then, and from there, he introduces a conclusion in which he says that uniformity of the Big Bang, and he denies, for instance, contrary to Hawking, the existence of the white holes because it would violate the second law of thermodynamics. And also from there, Penrose derives his very little supported by the scientific milieu hypothesis that there was no inflation. So actually, he is against the inflationary hypothesis, which he expresses quite clearly. And then, of course, then he bears this also controversial, which is controversial in the physics, idea that quantum mechanics is also incorrect, because he's very much, he shows this also in every single of his books, that if you have expression for the wave function, then the coefficients must be complex, and then without this you don't get quantum effects. And then what he says that quantum mechanics does not explain observation. So he actually takes very literally the formalism of quantum mechanics, and he says that it would have to be corrected somehow to reflect that we don't observe superpositions in microscopic reality. Okay, so basically this is where he becomes original as far as his claims based on his, I would say, even philosophy or ideology. And then this is an interesting quote from his book, The Nature of Space and Time, where the book which actually contains the discussion between him and Penrose, him and Stephen Hawking. And then this quote is interesting because it displays actually the way his ideology functions in deciding what kind of a universe we should have. So maybe I'll just read it slowly because it's interesting to look at it. From the point of view of the complex hieromorphic ideology, please observe that he uses the word ideology to indicate that his claims are not very much binding, but they're just proposals or even based on some subjective beliefs. From the point of view of the complex hieromorphic ideology of twistor theory, a Big Bang with the curvature constant less than 0, leading to an open universe, is to be preferred. So the reasons for preferring a k less than 0 are ideological. The reason is that only in k less than 0, universe is the symmetric group of the initial singularity, a holomorphic group. So for him, that complex number ideology here is decisive. Namely, just the Mobius group of holomorphic self-transformation of the Riemann sphere. This is the same group that twistor theory of I just missed some. Well, generally, the whole idea is that he makes his preference for k less than 0, saying that since this is based only on ideology, I can, of course, withdraw it in the future if I'm wrong, and the universe is, in fact, found to be closed. So you can see how his commitment to the idea of complex numbers, which he has argued, sort of drives his thinking even very deep into the proposals, what the universe should look like. And then here I presented a list of his disagreements, basically, which came up in the discussion with Stephen Hawking. But most of these disagreements are very unusual in physics. So I mean, you're probably more physicists than I am, and you will agree to this, that his proposals are controversial. But I think very much of that is driven by his complex number or hylomorphic ideology. So for example, this is what I said at the beginning, the status of the second law of thermodynamics and the symmetry of time at the fundamental level, CPT symmetry. So he would claim that second law is fundamental and there is an asymmetry of time at the fundamental level. Existence of white holes, of course, Penrose would say no, Hawking yes. And then there's something that I didn't go to, the information loss paradox. Penrose says it is complementary, so he still subscribes to it. But of course, we know that Stephen Hawking, although he proposed it at some point, he has recently withdrawn. Then, of course, inflationary hypothesis, Penrose will say no, Hawking yes, as many of the physicists. And then adequacy of quantum mechanics, again, Penrose will say no. And then many of the physicists, and of course, Hawking would say yes, based on his application of Feynman paths. And then, of course, Penrose will put forward his twistor theory as a proposal for quantum gravity. And then there's the long quote from a book which was actually a reprint of The Nature of Space and Time, which appeared in 2010. And the book was actually reprinted almost without any change. except for an addition at the end, sort of a comment at the end, which they both wrote in 2010, kind of looking from a distance at their discussion and taking into account all the different developments of physics. In this new afterword, we give a brief outline of where our respective views have taken us and of the central core of the disagreement between us. Perhaps the very fact that there is still be such a basic conflict of views, so they claim that still this conflict of views, with Penrose being a Platonist or a complex Pythagorean and Hawking a positivist. I mean, you would have to spend the whole lecture explaining what we mean when we say that Hawking is positivist. He's not a positivist in a Vienna Circle sense, definitely not. It's a bit of a distant idea, but I don't have time to go into the details of this. But they still claim that the divisions between them as far as philosophical standpoints are still in force and are not still binding. And even they claim that these divisions took them even farther away. So they say that there remains a healthy debate concerning deep and fascinating questions that concerned us about the fundamental nature of physical reality. And let me maybe go over some concluding remarks. And I would say that we could safely claim, and Penrose himself likes that, the idea that he qualifies as extended in the sense of contemporary mathematical structure, Pythagorean in the sense of the late Platonic school, right? So implying that we consider mathematics ontology. Because Penrose implies here on that graph a dualism, right? And I actually spent about 20 minutes asking him what he really implies by it and if he believes it this way. And I don't think, because he named it a mystery, I think what he really more closely himself believes is that they're not as separate, but I think his basic belief is that as you get down to the more fundamental level of reality, everything sort of evaporates and only mathematical structures remain. So that's actually the answer he gave me. I asked him specifically how he perceived that dualism, and he kind of got a bit of uncertain. Then he explained just by saying, yes, I think as we move down to the bottom level, to the fundamental level, so that everything, all the objects evaporate, and what you see is the mathematical structures. So I think this is the basic idea he holds, and that would very much fit with this whole complex Pythagorean approach. So he might be talking about mysteries here, but when you ask him personally, he admits maybe his views evolved now a little bit. He admits to something slightly different, more of a standpoint where you really think that the mathematical structures are at the bottom of reality. So this is. I mean, I think he's. At some points, he's quite. I found him to be quite uncertain, and he kind of talks about it in different ways. And then the two elements that I pointed out as being very typical of Pythagorean philosophy is the spatiality of numbers. And this is what I indicated, that you can actually, he equates the celestial sphere with the Riemann sphere, so you can basically touch the complex numbers. That's what his idea is. I think he comes this close. And then, of course, that whole idea of harmony, of the complex holomorphic structures harmonizing with reality. So that's a very old idea of the Pythagorean school. And of course, from what I was able to infer, that this twistor theory actually pretty much failed as a quantum gravity project. So actually, you would probably have to get critical whether really the complex structures, you can push complex structures as candidate for the fundamental ontology. And what I really noticed also, that the holomorphic philosophy very much drives his conformal psychic cosmology, which is also a vision which he published in his books the cycles of time, where you can actually visualize a sequence of universes as being as eons being connected through the singularity, which has a very very particular structure. And actually, I wrote a paper that it shouldn't be conformal cyclic cosmology, but a conformalist cyclic cosmology, meaning that actually the mathematical structure that are responsible for the transition between the different eons are really conformal structures, meaning they have a very close relation to complex numbers. So again, the holomorphic ideology just sits there. And I will just end my talk with a quick little reference to the third element of his ontology, which is the mind. And he maintains the standpoint that actually you're not going to move any way further in constructing a new theory of quantum gravity unless you will include the mental phenomena into account. I don't know how much he verified this hypothesis, because, for instance, in The Road to Reality, he talks very little about mind. But on the other, in the other appearances, he would stress very greatly the fact that we need this third picture, the third component of the threefold ontology, to really come up with the proper description of reality, as including both gravitational and quantum phenomena. So thank you very much for your attention, and hopefully we'll get some good discussion and questions. Thank you very much.